So we are starting chapter 13. Oh yeah, when you're walking out the door, when you're done, just turn in the bold words, right, for the reading, yeah, and the concept preview. Right. Okay. So we're starting with chapter 13, atomic structure and atomic spectra. So we're not talking about molecular structure. We're not talking about molecular spectra, just atomic. Right? If you remember, if you solve the Schrödinger equation, you get stuff like, what is going on here? 1s, 2s, right? 3s. When you're walking out the door, right? As energy goes up. But I'm kind of writing. The number was called the principal. Like the 1, the 2, or the 3 is called the principal what? Quantum number, principal quantum number. And they call these shells because they're all at the same energy right now. So those are called shells. So this is the idea of electronic structure, right? For an atom, not a molecule, for an atom. Okay. And if we have a hydrogenic atom, let's go over to here and take a look at it quick. Come on, let's go take a look at it. So I want to do this in a dark room for once.
These things.
Yeah.
Hurry up, Ricky.
So grab one of these. Okay. Yeah. So we've looked at lights before. We have had plenty of experience doing this in a non-dark room. So let's do it in a dark room. All right. Now first, orient this thing right though. First, right? Remember, the slit has to be towards that. Okay. So find the slit.
Oh, this one?
That slit has to be lined up with that. Okay. Let's see if this works better. I haven't done this before either. Oh, we can't get it totally dark in here. Oh, we can't get it totally dark in here still. Where is it?
I only see like a red line.
Yeah.
Oh,
They're really hard to see. But if you get that lamp in there, all you will see is that red line. But if you look way over to the right.
Yeah, I see it to the left.
Yeah, I see it to the left.
Or the left,
spectrum?
yeah.
I see the left and the right, that's why.
Really?
Yeah.
Well, you're right there, Ricky. You're blocking over.
Oh yeah, left is easier. Left is easier, right? Okay, but you still see a little bit of a blur, and that's probably from this stuff and from up there. But the point is that there's lines. Okay, so that was a lot easier than.
And what were those lines?
Exactly. Let's go to. That's our electronic structure,
The class.
right? That's our electronic structure. For molecules or atoms? Atoms, exactly.
What element was that in that line?
That was hydrogen. So at a really now does hydrogen exist as H2 or H in nature? H2. So at that extremely high voltage that you saw this glowing, that was not H2 molecules. That was hydrogen atoms. They were actually split. And then they emitted their light, then they somehow got back together. And we're not talking about a lot of them, right? Because your eye is extremely sensitive. You don't need very many photons to detect it. Okay. So you saw the spectrum, and it can kind of look like on page, if you have your book, if not, I'll show you. Page 344 in the book, they kind of made a plot of them. When you read it over, I'm sure you saw it. Right, this guy on the bottom, and then what they did is on the top they had all the lines, so they had a much better detector and room than our eyeball was over there. But the point is they had all the lines, and then they have Balmer, Lyman, Pasch, all these different series, and they're just playing around with different little rules, trying to get, because they know it's changes in energy states. So are there some simple expressions you can use to explain those lines? And that's where, and the guys who figured out these simple mathematical relationships between different series, and if you add up all the series, you get the total, right? So we're not really worried about all these different series, but in this, in this equation right here, we've got all of them, okay? And that's where this is coming from. All the Lyman series. I think some of these guys were high school science teachers. So if you just plug in n1 equals 1, right, and then you can get all the different, ooh, what's that symbol? Frequency with a tilde. That's called a tilde. That's our wave number. And wave number actually had what units? That the wavelength did. Right? If we had, for example, our Bohr frequency condition. Let's jump down here. Our Bohr frequency condition. Well, let's finish the question with wave number first. H C over lambda, right? Which would be H C times wave number. Why? Because what's wave number? What were its units? Like if you go into the FTIR, that x-axis, what are the units? They're wave number, but you ever look? And in all the tables, the carbonyl stretch, the OH stretch, it's inverse centimeters. So wave number is just 1 over wavelength. Now you remember, if you want energy in what units? Joules. Everything has to be in standard metric units. You can't be using inverse wave numbers. You're going to have to convert, but that's fine. Okay. So, and they don't have E anymore. Before we used to say E equals H nu. And conceptually, that was the energy of a photon, right? Okay, now they're just saying, oh, okay, we're just changing the concept a little bit, that energy of the photon is going to exactly match what? Go up into one of these lines. How are one of these lines generated, right? Like in that hydrogen atom. These guys are fixed, these energy states. So if that photon exactly matches that energy difference, oh, it'll absorb. It'll emit that exact same wavelength. Okay? As long as these are your only two energy states. It'll be that simple. Okay, so they changed the E to a delta E, saying that, okay, the energy difference between the states has to match. Make sense? And then really what this chapter is all about, there was some song with Ritz. Do you remember this a long time ago? I should look that up. That would wake you up in the morning. It was a snappy little song that stuck in your head. It's really old. I'll get it next time. But the Ritz combination principle is really the goal of this entire chapter. It's not the singer guy group, but what they say is that our big goal is we are going to write a term symbol to describe each of these states. We're going to write a term symbol to describe every state in this atom. Ground state, all the excited states. And by looking at that term symbol, we can say, hey, that transition will occur, or that transition will not occur. That's the Ritz combination principle. So that is the big goal for this chapter. And there's no way we're going to get there today. But we'll get started on it anyway. Okay. And then the structure of hydrogenic atoms. So remember, this whole chapter is not about molecules, it's about atoms. And now this section 13.1 is about hydrogenic atoms. So Ricky, what's so special about a hydrogenic atom? What are they trying to say?
Just a proton?
Well, a proton with how many electrons? One. No more than one. So that's all they're saying. So you could be a lithium plus 2. This would work. So hydrogenic atoms. You can have an atom, but only how many electrons? 1. So hydrogen is the only one that's going to be neutral. Everything else you can have, it's going to be a cation. But the point is, you can only have one electron in this atom. Okay. Now, let's see who remembers their concept preview here. We have a hydrogenic atom. So that means we've got a nucleus and a electron. Okay. So we need to be using reduced mass when we want to distinguish between, maybe this isn't a good example. Okay, we want to use reduced mass when we do this. I'm going to attach a weight to the end of two springs, a weight to the end of each spring, right? And I'm just going to whip that blasted thing across the room. Okay, and there are different weights on the ends, and I'm going to whip it across the room to Ashley, and she's going to catch it. So if we want to talk about its trajectory or how fast it's going, it's just mass. Mass the whole dang thing. But no, what if you want to talk about, as this thing is flying through the air, what is it doing? It's intermolecular motion, or intramolecular motion. It's vibrations or its rotation. You want to talk about what's going on within the molecule itself, you can't be using mass anymore. You have to be using, what's the word? Not mass, but reduced mass. Okay, now all we have is a nucleus and a electron, because it's hydrogenic atoms. Which one's more massive? Proton. A proton, well, the nucleus, right, the nucleus in general. But if it's hydrogen, if it's hydrogenic, we should say nucleus. If it's hydrogen, we should say a proton. If we have a proton is how many times more massive than an electron? You can look in the inside front cover of your book, and because they say the masses of them. And that's the only way I can answer this question, is I looked at it, and it's about 10,000. So a proton is about 10,000 times more massive than an electron. It's not gadzooks a lot, but it's a good amount more. In the concept preview, Richie, we did this. We said, hey, M1 is much, much less than M2. We did the math. The reduced mass is equal to which one? What is the answer? M1 is much, much less than M2. So all we have is two objects to worry about, just like a hydrogen atom. It was M1. It was the lighter one. You do the math. You do the math, and then, yeah, some concept is probably chapter 12, because there's going to be a lot of chapter 12 stuff in this. So it reduces down to M1. Okay. So if you get on the show, Are You Smarter Than a Fifth Grader or whatever, and they say draw a hydrogen atom, right? If they say draw a hydrogen atom, right, hopefully you won't draw the Bohr model. What is the Bohr model? Because it's totally wrong, but it's very convenient. It is so convenient to answer all of these questions. And we were even stuck still on the Bohr radius here. The most probable radius of the electron and the hydrogen atom is the Bohr radius, A0. And we did that. We calculated something like that. But what is the Bohr model? Do you remember what it was, Ricky? What was it? In the very center, you have the what? The nucleus. And then you have the what going around it? The electron.
Is it like just like a circle around?
Exactly. Okay, here's one orbit. Here's another possible orbit, right? And we should probably draw on dashed lines or something, because they're just possible, right? So, and this model is supposed to be totally wrong. But doesn't it, if you think about this expression, doesn't it really answer this extremely well? How you generate all those different lines? Richie, or not? To me it does. Why does it? Why would the Bohr model, ooh, man, this makes so much sense. Even to a fifth grader, I bet.
What's up with that RH thing up there, that B?
Oh, who cares? Rydberg constant. What do you, if it's any constant, what do you do if you don't know what it is? Look it up. So you don't care what the hell that is. Why are you stuck on that? That's just an expression to get all the different wave numbers. right? For each line in the hydrogen atom. So you can plug each wave number in, get the energy.
Can you repeat your question?
Why does the Bohr model explain that spectrum right here in the book? Page 13.1. What you saw over in that dark room. Why does the Bohr model explain it so well?
Because something's increasing as you go along with
What
your
what can
numbers,
how does a Bohr model generate those lines?
the radius?
What does it do? What's the difference between this orbit and an inner orbit? What's the difference?
The size.
As you go farther out in different orbits, are they all the same energy? No. That's idea number one that works great. Quantized energy. As you go further out, more energy. Aren't these fixed energies? Yeah. So how could I generate a line? Just one line that you saw. How could I generate it using this Bohr model? The electron could be where? Not in its what state? It could be in, I don't care, pick a state. Any state out here. Any excited state. Then what does it do? Right? What does that? It jumps. It jumps from this orbit to that orbit. Maybe you get red. Okay, well, let's not jump from that orbit to that orbit. Let's jump from this orbit to that orbit. Get a different color.
So then, like, depends on what excited state it'll
Yeah, you can get different, or you could jump from one excited state to another excited state.
and it'll change the color.
Right? So that it's a great model. Right? That answers all the questions. What about if you have a different hydrogenic atom? Well, heck, then you just have different orbits. Right? Because it makes sense because it's a different nucleus. It has a different charge, has more neutrons, protons. It should have different trajectories. Okay, so this Bohr model works great for conceptually understanding the series. What's wrong with it then? What's wrong with it?
The shape of it?
You did a whole lab on it, Ricky. You even wrote the equation for it. Whose principle? Heisenberg, exactly. Heisenberg uncertainty principle, which everything is based on pretty much in quantum mechanics. And that was pretty much, is this possible to know the trajectory of an electron? It's not possible. Because then you'd know where it's at and you know its energy. You can't do that. You can't, no. The more you narrow it down where it's at, the less idea you have about its energy. That's the whole idea of the principle. The more you want to know about its energy, the less idea you have where it is. So, no. If you get on the show, Are You Smarter Than a Third Grader? Or was it fifth grader? They say draw an atom. What should you draw? No! That's what this whole talk is about. That's how you lose. That's how you lose. If I was the teacher of the fifth grader guy, what do you draw?
That's right.
According to our model right now, it's a pretty slimy answer. It's a pretty slimy answer. And you guys know this answer. Draw a big blob that's maybe dark in the center and get it kind of lighter out here. I can't draw lighter. What am I trying to draw? And then say, oh, about 90% of the time the electron's in there. What am I trying to draw? A model of a, starts with an O, what we call them. Bohr called these orbits. We call these orbitals, right? So you have all these solutions to our hydrogen. We have like, this is kind of that, I'm trying to draw a sphere where it's darkest in the center. It kind of gets, you've seen the models of the, like the 1s orbital. Yeah, so about 90% of the time it's there. That's all you do when you're drawing a model, okay? For an atomic orbital. So, well, there's no way they're going to talk about that in fifth grade. Okay. So atomic orbitals. So if we solve the Schrödinger equation for which atom? and this was done, how do you spell Schrödinger? S-C-H. You solve the Schrödinger equation for which atom? And you get all these atomic orbitals. Which atom did they solve the hydrogen? I said it. The hydrogen, right? They solved the hydrogen atom. And why? Really, they solved hydrogenic. Why? What's the big complication here? It's hard for you to answer that without actually getting stuck doing the math, but it's those electrons. The electrons are the issue. And in the Schrödinger equation, remember you're trying to get those energies? That was the which operator? What do we call this? The Hamiltonian. And inside the Hamiltonian you had to know what V was. How to describe this potential energy. And there's your issue. If you get more than one electron, you get these electron-electron interactions, and that's just really ugly, really fast, even with 2 electrons. So hydrogenic, great. Man, we're actually dealing with absolute answers here. Atomic orbitals. Okay. And you've heard of the names, 1s, 2s, 2p, and all that went along with it, right? And the solutions were like, remember you had little n, and we talked about this in our concept preview. We talked about what n could be. We talked about what L could be, and M sub L, all those rules. It's really just statistics, what it came down to. Okay. And we found out that for any n, how many orbitals were there? What did we say?
Squared.
N squared. Yeah. Oh, what was another one? Well, how about for any L, there are how many orbitals? How many orbitals?
Negative L to L.
It goes negative L to L.
Compound. Just add all.
So add them all up, you always end up with 2L plus 1.
Yeah.
All right? If you pick an L,
Okay.
you're right. It goes from negative L to L, all the different M sub L's, right? What is L? If you pick an L, what are all the different possible M sub L's? They go from negative L to positive L. So add up all those, and you get 2L plus 1 orbitals. So you get a different M sub L, you have a different orbital. All right, that's kind of like, remember, okay, well, we talked about that. Let's see. This Bohr radius, it's in the book, but I just want to put a number on it. 52 picometers. What's pico? 10 to the negative 12. Yep. Okay. I guess we didn't really talk about this.
Why'd you mention picometers?
Oh, just because that's what A naught was.
Oh.
If you look it up in the book, it's 52 picometers. That's what A naught is. They call it the Bohr radius, the most likely radius. Principal quantum number. Okay. So we have all these different quantum numbers, right? But for hydrogenic atoms, the energy, here's the energy for these shells, right? The energy only depends on what quantum number? Do you recognize it in there? The N. You don't see an L, you don't see an M sub L. So that means all those are degenerate, right? All the energy only depends on the N. So the H, the C, you've seen before. What about Z? Ashley, what do you think Z is going to be? Atomic number. So, I don't know, what's the atomic number of magnesium? Just to make sure you're on the same track as me. What's the atomic number of magnesium? 12, yeah. It's the number of protons in the number of protons in the nucleus. Remember, you just change the number of neutrons, you're just messing with making things stable. So atomic number just has to do with the number of protons. Nothing to do with the number of electrons. We've seen R before. That's what Ricky was hung up on, right? that Rydberg constant. Okay, remember seeing that? And when you're interested in what it is, you just got to look it up. Okay. Now, one thing that's kind of odd, I think that's odd, is you ever hear of, you calculate the energy of a baseball flying through the air, and you get a negative number. Wouldn't you just delete it, right? Every single energy that we're talking about is what? Negative. You don't get a negative number here, you're messed up. Why? All of our energies are negative. And they did this on purpose. They're trying to, it's from physics. If you talk about the energy of repulsion, two like charges, convention was, that's positive. If you're talking about energy of attraction, that's negative, right? You got to give it some number, and they give it negative energy. That's just how they did it. So the more negative that energy is, the stronger or weaker the attraction. Which one would it be? Stronger the attraction. So they start talking about wells and how, oh, you're deeper down in the energy well, which is a good thing. The ground state should be at the very bottom. Right. So that's kind of what this is, a slice of your potential energy well. Okay? And now if you can, your notes might be better, but all they did is, here's n equals 1. So they substituted n equals 1 into here, and then they wrote their answer. Negative HCr. I don't know if I can draw that fancy R thing, but, right? So that means Z must be equal to, what Z must, if I want to substitute and get a negative HCr out of this, what does Z have to be? Has to be 1. So they're talking about which atom then? Hydrogens. This is the model for the hydrogen atom. Do the energies look equally spaced? No. Then they have this broad blue line through this whole mess here. And they call it a continuum. They're just trying to hit on the fact that, dang, remember, energy is quantized. So you can't take any energy you want. So if you want to talk about continuum energy, yeah, that's just this constant blob. You can take on any energy you want. But once you get above, right, E equals 0, then you can take on whatever energy you want. You're free. It would be, see how they have H plus E minus? What do you call that? That's the I word. You're ionizing it. So you can give that electron, it's free. There aren't any boundary conditions. So if there are no boundary conditions, it can take on whatever energy it wants. Okay, it's not bound. Because remember, I think it was on exam 1. This quantization comes out of what conditions? Boundary conditions. If you don't have any boundary conditions, you can take on whatever energy you want. So that's true. Okay, you reach once you're ionized. Okay, you can't see any spectroscopy because there aren't everything's right. There aren't any boundary conditions. Okay. So unbound states, that's the continuum they were talking about. Ground state. We talked about shell. Now they're using the word subshell. Shell was when you had the same which quantum number? The same, what did I say? The same principal quantum number, which is what symbol? N. Subshell. Well, that means now you must have the same L. Okay. So subshell means you just have the same L. Okay. and they kind of listed out their shells here, are the 2s, just to practice our terminology here, the 3s, the 3p, the 3d, they are all the D word. They're all degenerate, according to this table, right? For a hydrogenic atom, they're all degenerate. So then they started, okay, what are these wave functions or boundary surface, the probability, the radial distribution function, P of? What does it look like? What do these models look like? Now, it's hard to say that this is actually true. They're just saying that they're just trying to give some visualization to what the math is doing and what the math says. And it gives some really peculiar answers. Like, look at like you have a lobe here and a lobe here. One's positive, one's negative. That's just kind of, they do that a lot. And if you really dig into it, that's really just the sign of the wave function. The sign of the wave function changed. But what do we call this in the very center? The very center, what do we call that? A node. Now, a better word for that now is angular node. All right? Or a nodal plane. Because now we're into 3 dimensions now. And I like the idea of angular node better because the number of angular nodes is really just L. If you pick a different L, you'll have a different number of angular nodes. The more nodes you have in any standing wave, the higher the energy or the lower energy to create all those nodes. Higher the energy. Remember the slinky? We had to really get it going, but we got more nodes. Okay. Okay. The radial distribution function, P of R. Okay. So what they're trying to say is this is just a probability of finding it kind of like in an eggshell. You have pick your orbital, right? And just kind of imagine an eggshell at different radii. What's the probability of the electron, being in that eggshell of thickness dr, right? That's kind of what this radial distribution function is. Okay, so this is kind of what it looks like. That right around r equals a naught. When you have a 1 here, because notice how the book does this a lot. That means that you have to divide whatever the axis is, right? That means like 2 has to equal r over a naught. They do this a lot. So then r equals 2a naught. That's what you're supposed to see. I don't know why they just don't write. That's author's conventions. We just got to get you're going to see this a lot. So this would be 2a naught right here. So whatever the x-axis is, you set it kind of equal to their units. So, but notice the maximum is lined up right with a naught. And that's what it's supposed to be, the Bohr radius. Okay. So if we want to calculate the most probable radius, that's why they set up the radial distribution function this way. Oh, you don't have the function. Oh, there it is. It ended up way over here. This should be under here. The radial distribution function is this P of R, and how do you get it? Take R squared times your radial wave function, R of R. That's down here. So that R of R you just pretty much have to look up in a book. But if they ask for most probable radius, just take the derivative of this function, P of R, and set it equal to 0. Okay. And remember, P of R is this function right here. That radial wave function, you just got to look it up. It's on page 349. Table 13.1. All right, page 349. What does that look like? There's a bunch of them. Okay. So in that table, it looks like you'll have a different radial. It has a little subscript NL. So pick an N, pick an L, then you can look it up. You know exactly what it is in the table. Okay. So it's nothing you memorize. You just kind of look it up. Obviously. Full wave function for hydrogenic atoms. All right? Here's the full wave function for hydrogenic atoms. That's how they got all this information from. R of R, and then we've seen this part before. This was the, I don't know if you remember the name, spherical harmonics. And that's way back on table 12.3, page 334. And we did a few of those back in chapter 12. Let's see if you remember. It was this table that looked like this over on the side, where you picked an L and an M sub L, and you looked up the different Y. Yeah, well, I guess it kind of tells here in the subscripts. Okay, that had theta and phi in it. It's a lot easier to work in spherical polar coordinates with this stuff than X, Y, Z. Okay, we're almost done here. So to find the most probable radius, we've got that one. But what about to find extrema? Let's do that one. To find radial extrema. Right? Minimum and maximum. There, we're going to take the derivative of just the radial distribution function and set it equal to 0. And then what if you want to find nodes? You want to find radial nodes. Exactly. Just set the function equal to 0. Don't take any derivatives. Page 349. What's this? Okay. So, for example, on page 349, they plotted out some of their radial distribution functions, and right, the nodes are going to be where it crosses 0. Okay, but you're not going to go through all the work of plotting this thing out and seeing where it crosses 0. You just set the wave function, set the radial wave function equal to 0 and solve for it. Okay. So what we are at, okay, this is where we are. We're gonna stop here, and this is where we're gonna pick up on Monday at this section 13.3. Through, I'm trying to read my notes here, through number 4. Oh yeah, there's a line here. So this is where you stop for your homework. Okay, so homework for Monday, stop at that line. So you do all this stuff.
So go ahead and do,
okay.
Go ahead and do above the line.
So let's take a look at this. Additional assignment.
Everything above the line, nothing below it.
Let's write the wave function for an electron in a 1s orbital. Okay. And then we want to calculate the most probable radius. Now, the electron for a 1s orbital, this will be good practice. So that means we have to follow, right? R of R, Y, L, M sub L. Okay. Okay, so I lost where I said these tables were. Page 349, table 13.1. That's where we find R of R. Right? Oh, you want to look it up for the 1s. Page 349. All right. So do you see it? Well, you don't have your book. Okay, I'll copy it down for you then.
Sorry.
What I'm going to do is I'm going to just copy it. So this is from page 349, table 13.1. For the 1s, I'm writing down the r, the radial distribution function part, just copying it verbatim. 2 times z over a naught. Now, what's z again?
Charge.
Atomic number. E to the negative rho over 2. Now, this is where it would be good for you to have your book, so you can not depend on trying to read my English here or my Greek, trying to read my Greek. That's supposed to be a rho. How do you draw a rho? Right? You know, like the density symbol, rho, kind of a squiggly looking P. And then if you read down further in the table, it tells you what rho is. Rho is 2zr over a naught. That's what your rho is. Okay. And then now I have to get my spherical harmonics part, and that is from table 12.3, page 334. So page 334. Okay. Now I'm supposed to be writing it for the 1s. Right? Now my table only has L and m sub L in it. I have to look up an L and m. What would I look up? What values would I be looking up then? Right? How do you figure that out?
How do you find L?
Yeah.
What's that Y again?
Spherical harmonics. You have to look it up in the table.
Yeah.
And they're all listed by different L's and m sub L's.
What's it up in?
You can't. You need to know what the L and m sub L are. Concept preview.
Let's go
Oh,
back.
12, right? 1s would be 0.
For any S, L is
0.
0. Right.
For any
So
S.
Yeah, because that means p would be 1 and so on.
if P is 1, sorry,
Oh,
if you have
so
P, then L is, if it's a P orbital, L has to be
1?
1. If it's a D,
it's gotta be 2.
L has to be 2. If it's an F, L has to be 3. Remember that? Okay. So if, what do these quantum numbers L and m sub L have to be then?
Both 0.
Why are they both 0?
Well, if L is 0, then m sub L has to be 0. Negative L to the positive.
Exactly. Listen to Richie. He's got it. Explain to him again.
If L is 0, then that means m sub L has to be 0 because that's negative L, positive L.
Okay. So I have to look up my spherical harmonic for 0, 0. So I look it up, and it's just 1 over 4 pi square root. Okay. Okay, so this is what my my wave function is. I'm trying to draw that fancy, this guy. I'm not very good at it, right? Trying to draw a capital psi. Okay, just trying to distinguish that between little psi. You'll see why in a little, probably in the next day or so. We'll see why we have capital psi and little psi. But okay, here's my complete wave function. The problem was not to write the wave function. The problem was calculate the most probable radius. So how do we do that again? What was the idea? there's pretty much 3 tricks here. Right? There's one here. There's one here. Right? There's another one here. Because you can find radial extrema, you can find nodes, and you have a game plan for finding most probable radius. So we should follow a game plan for finding right? Yeah, it's got to be this one because they want us to find the most probable radius. So it has to be this one. So the first thing I would write, because there's so much math, you don't want to screw up in the very beginning, so write it, just like we always did. Another starting point. Okay? And then you follow the math. What was P of R again? All right, what are these expressions? Where'd it go? You see it? What was P of R? R squared times, what do we call it? R squared times the radial distribution function, right? So you use the terminology because that'll really help you. That'll give some meaning to all this, right? The most the radial wave function, not the radial distribution function was P of R, right? So that's P of R. So this is the radial, what do we call it? The radial wave function. Radial wave function, and we got to square it, take it times R squared. That would be P of R. So we have to take the derivative of R squared times our radial distribution function. That has to be squared too. And set it equal to 0. So we didn't need all this stuff. All we needed was this first part. That's our R. Right? Remember when we looked this up? You multiply that times y, so that means that part must be this. So we'll take R squared times this, set it equal to 0. Does that look familiar? You did this in the concept preview.
Yeah, it's like that infinity to infinity deal.
No. You did this exact problem in the concept preview. You did this. All you do is, right, take these two, write this function in here. Now, do you see an R in here? Yeah, remember what rho is? So it's the derivative of the first times the second plus the derivative of the second times the first. We'll go through the math. It's the exact same concept preview question, right? We did this. So it'd be good practice for you to do it again because it's not you're not comfortable with it. So, but you pretty much follow the math. Don't like you wanted to, Ricky. You wanted to do an integral, and pretty much the only reason why you want to do an integral is because of habit, right? Habit said, oh, almost everything's an integral. No, follow the math. The math just says take the derivative of this and set it equal to 0. So that's what you got to do. What is this? Look up the equation for it and substitute it in. Well, what is this? Look up the equation for it. It says multiply it by R squared, so you got to do that, right? It's almost like blind faith following math because it's very specific as to what you have to do. You don't do anything extra. So we substitute in our R, and then you got to see, oh, well, you take the derivative with respect to R, so that'd be, well, is there any little r's in this? Yeah, there is, because remember what rho is. So it's pretty much exactly that concept preview question, which you have to turn in. So that means you got to do it all again. It would be good practice. Okay, so we're about out of time. So
We just solve for wherever. Wherever R equals
Yeah, you're going to end up with finding r equals something. Take a look at your concept preview. You did this exact question. Because you got to turn it in, so one last little chance to look at it and see how you did it.
Take a picture. And we're just trying to find the minimum and maximum?
Extrema. Yeah, you'd pretty much, since we just took the first derivative, if you want to know whether it's a minima or a maxima, you pretty much have to go and plug it back in and see if it is a minimum or maximum. Or you could take the second, remember the tricks? You could take the second derivative.
Yeah,
that's too much trouble. You're just going to end up with one answer, so you don't need to worry about it.